Okay, so today what we're going to do is try to come up with a mathematical representation for what the most common or most likely speed would be regarding the Maxwell Boltzmann distribution, which is going to represent an ideal gas situation in which we've got like a constant temperature, pressure, and volume, recalling the Maxwell Boltzmann distribution. We'll call the likelihood that a particular temperature, the likelihood that a particular velocity could be found in any particle and within a gas at this pressure, volume, and temperature. In this case, we want the most likely one. There's another word for this. It's V mode. It's the one that corresponds to the highest probability in the F direction. So, given the Maxwell-Boltzmann distribution in one dimension, we'll call it the X direction, however you want to think about it. So this is a Boltzmann's constant at K, and this T is temperature. M is the mass of the particle. And we are going to just consider this as the X direction in the exponential part of this equation. All right, so recalling that V total squared is equal to Vx squared plus Vy squared plus Vz squared. We are going to have to translate this form, which only has the Vx form, and somehow magically add these in order to get a representation for V total. Well, luckily in physics, you don't have to be very good at magic. You just have to think. So here, if we considered this as a constant called alpha, and we multiplied this entire function by the spatial dimension for y and z in an exponential form, so alpha vy squared and e to the alpha vz squared, by the rules of exponents, exponent arithmetic rules, we're going to have the same constant in the front, this e is going to be v total squared now, with a minus sign, and still multiplied by alpha. And we are going to have to put something in here, recalling that the line element for spherical coordinates is going to have dr direction, a phi direction, and sorry, I think I misspoke, a theta direction here and a phi direction element here. Combining this together, we get the volume element, r squared sine phi, dr d phi d theta, and looking at this part right over here, v squared total. In our case, we are going to consider this r as v squared. So this is the one in question. And from this, 0 to 2 pi is just 2 pi. From this infinitesimal element, we are going to get a 2 from 0 to pi. And then we are left over with an r squared, which is the one in question, which actually will be changing. So we have to put in a 4 pi r squared here, but we'll call this v total. Now, in order to find this point of zero slope, there's a calculus trick that we can do. It's called setting the derivative equal to 0. So here we have dv by dv total of f, this function over here. Let's pull out everything that is not doesn't have a relation to v. So we'll have the big constant. I'll write it out instead of using alpha, just for more clarity. Alright, times 4 pi. And now we'll write the derivative operator and everything that concerns us with v. Okay, now setting this to 0, we can perform this operation right over here. So this looks like it's going to be a basic product rule, in which we just do the derivative of the first multiplied by the second product plus the first product multiplied by the derivative of the second product. So calling this the constant, we have ddv total of f is equal to the constant multiplied by the derivative of the first, which is 2v, times e to the minus alpha. Remember, we called alpha all of this stuff. V squared plus v squared to the minus alpha e to the minus alpha v squared times another 2v for chain rule. Okay, so what we're going to do here, yeah, this is still set to 0, is, well, I'll start a fresh page and we'll just do some arithmetic with this piece. From where we were at, we were setting the derivative of Boltzmann's distribution with respect to the total velocity. Oops, that doesn't look very good. So this is the m over 2 pi kt, Boltzmann's constant times the temperature, 3 over 2. And we had the 4 pi from the three-dimensional transformation that we did from the original one-dimensional Boltzmann distribution. And we had to derive this. Okay, so we were on this part where we were handling the derivative, and we saw that it was going to be a product rule, and we did that out. So I think I'm just going to let beta equal m over 2 Boltzmann's constant times t. So using this new beta notation, let's say that beta over pi, I'm thinking about this part over here with all of that, to the 3 over 2, multiplied by this 4 pi, multiplied by the derivative of this, which we talked about. So derivative of this is 2 pi times this, plus this one times the derivative of this, which is e to the x dx. So we have a chain rule in there. 2v e to the minus bv squared plus v squared and the chain rule guy, which is e to the x, so e to the x, and the dx part will be minus b, and the chain rule part will be 2v, from having to do the chain rule on this again. If any of that was too confused, well, I guess I should just do it because these are tutorial videos. So, okay, so the problem here, instead of doing it mentally, is for some of you who might have gotten confused, was like, oh, how do I take the derivative of this one with respect to v? So how I would do that is I would set like a u substitution, and let's let u equal to v squared. So du would be equal to 2v times the derivative of v. Okay, so in this case here, we would have e to the minus b times u, and we know that the derivative of e to the x, let me write it over here. So e to the x, when you do d dx, you get e to the x times dx. So in this case, we have e to the u times du. So we have du over 2 is equal to v times dv. And du by dv is actually equal to 2v. So what we're doing here is we're saying let this guy be u. And how does u change with respect to v? So the du by dv part is over here. It changes by 2v. So what we're doing over here is we're saying e to the u times du dv. And that's how we get this representation over here. So continuing from that point, trying to recollect all of our thoughts. We would have 0 is equal to 4 pi times b over pi to the 3 over 2. Let's go ahead and factor out this, because we see that in both terms. E to the minus bv squared, 2v minus b changes this, times another 2, and the v and v squared here will become sorry, this v and this v over this v squared and this v will become a v cubed. And we can divide all of this stuff over here, constants, and get 0 is equal to e to the minus b v total squared times 2v minus 2b v 3 to the power of 3. And we have to find out when this is equal to 0. So considering that we know information about the exponential function, we know that it's not this piece that will ever cause this to be 0. This is a rapidly growing function, in growing in more and more negative values. Regardless, this will not help us achieve our goal of reaching 0. But this one will. And whenever this is equal to 0, whatever the exponential part is, doesn't really matter very much to us. So just setting this p is equal to 0, we can see that we have 2v is equal to 2bv cubed. Getting rid of the common 2's and dividing by the v, we can see that we're left with 1 is equal to bv squared. Now, recalling that b is equal to m over 2kt, let's move this onto this side by division so that we have 2kt over m is equal to v total squared. And let's square root this side, get rid of this, and we have a representation for the velocity that will correspond to the highest value of f when we consider that f is the Maxwell Boltzmann distribution. When we asked, hey function, where is your value the most maximum by examining the derivative? And this is actually v mode.